Hey folks, all right, I got two more examples for you of calculating capacitance. And the first one is a coax cable, which is uh, coaxial cylinders, conducting cylinders. So we have an inner metal shell, and then we have an outer metal shell. They're concentric. You've taken electrons off of the center shell and moved them onto the outer shell. Okay. Uh, this thing has a length L, it has an inner radius A and an outer radius B. So again, you have hollow regions. You have this area here is hollow. Now, by the way, it could be solid, doesn't really matter. And then you have this region here that is also hollow. There's nothing there. Okay. If you need a minute, go ahead and copy that diagram down real carefully, and then we'll calculate its capacitance. All right. So, how do you calculate the capacitance of this arrangement? Okay. Well, you first have to know the electric field in there. It's a chapter 24 thing, right? Okay. So you're going to use Gauss's law. So if you remember Gauss's law, double integral closed surface E dot dA equals Qn over epsilon naught. And I'm going to go through this part real fast because it's total review. We're going to draw a Gaussian surface that is concentric with these two cylinders um, in between those two cylinders. So you end up with E, the um, the lateral area of that cylinder would be 2 pi r times L, okay? That equals Qn, which is lambda L over epsilon naught, okay? And if you solve for E there, the L drops out. You get E is equal to lambda over 2 pi epsilon naught r, or the otherwise equals k lambda, or sorry, 2k lambda over r. Okay, so that's your electric field. And then in chapter 25, okay, we had to figure out change in voltage from B to A, okay, which is negative the integral of E dot dr, okay. Now when we do this, you get, again, I'm going this quick because this is something we've done before. You get negative the integral of 2k lambda over r dr, okay. And if you integrate that, so the negative 2 and the k and the lambda are all constants, you're integrating dr over r, which is simply natural log of r, and you're evaluating that from B to A. And if you do this, you get delta V is 2k lambda natural log of A over B. Whoops, scratch that. It's natural log of B over A. It's negative natural log of A over B, which turns into positive natural log of B over A. So that's your change in voltage. That's chapter 25. Now we do the new stuff, which is actually the easiest part, chapter 26. Capacitance is defined as charge divided by change in voltage. The charge that we got on this inner conductor is lambda times L. Okay, so we've got lambda L over that change in voltage, which is 2k lambda natural log of B over A. Okay, the lambdas drop out as they should, because again, the how good something is at storing charge should not depend on how much charge you've already put on it. And you get the capacitance is equal to L over 2k natural log of B over A. Okay. Now again, a note. The longer the cylinder, the better the capacitance. So if you were to double the length of this, it would have double the capacitance. In other words, for the same voltage, you would have twice the charge move, twice the electrons move from the inner shell to the outer shell. Okay. And then the closer B is to A, the closer natural log becomes 0. So this approaches 0 as B approaches A, and as this approaches 0, capacitance approaches infinity. In other words, the closer together you can make these, the bigger your capacitance gets. And we talked about that in the last video. We talked about the closer the two conductors are, the better. Okay, so there's an example and that shows up. So while finding capacitance by itself is pretty easy, you have to remember your how to find electric fields and how to find changes in voltage in order to get to this point. Okay. The last example is a parallel plate capacitor, which is probably the simplest one. Okay. So let's say you have two parallel plates of metal, okay, like so. And here's the other one. All right. And you hook a battery up such that one plate ends up with a negative charge density sigma and the other plate has a positive charge density sigma. So you hook this up, electrons went flying that way off of the right-hand plate onto the left-hand plate. Okay, and let's say the plates have an area A and they're separated by a distance D. Okay. All right, so in chapter 24, we learned, and I'm not going to repeat the whole thing, but we did learn that electric field between two parallel oppositely charged plates is sigma over epsilon naught. Okay. And then looking at chapter 25, change in voltage would be E times the D. Now, I'm not doing the integral here because the electric field here would be constant, right? It would go from the left plate and there'd be straight lines to the right plate like so. So because the electric field is nice and constant in there like this, okay, you don't have to do an integral. Like up here, we had to do integrals because of the electric field was not constant. Well, here the field is a constant number, so you just multiply. And you get the magnitude of the change in voltage is a sigma d over epsilon naught. Okay, and then we do our chapter 26 stuff. Okay, so capacitance is defined as how much charge you have divided by the change in voltage. So how much charge is on one plate? Well, it's sigma times A. Okay, so our capacitance here would be sigma A over the change in voltage, which is sigma D over epsilon naught. The sigmas cancel and you get epsilon naught A over D. Okay, so that's your capacitance of two parallel plates. There's nothing in between them. Again, same thing as the other two examples. The bigger the area of the plate, the better. And the smaller the distance between the plates, the better. Okay. All right, so I hope these two examples were helpful, and thank you very much.